This is where we left off last time. We're talking about phase transition. So this is physical transitions. That's a transition. I'll call it transformations. I think that's what I said last time. So not chemical yet, but we're going to get there. We're going to skip a bunch of stuff because I do want to get to chemistry. So we're going to focus on main ideas even more. But here's a main idea. As I said, if I take a sealed container, probably a cork wouldn't be good enough, but we have a sealed container so nothing can get in or out. And I put a vacuum in there, and somehow I have a Mr. Scott beam using a transporter, a block of ice into that thing. You know what I'm talking about? Star Trek? Yeah, okay. And then the ice is in there, and there's a vacuum, and heat can get in, and so it can come to room temperature. That ice is going to melt, and eventually, probably all hell will break loose if I actually did that. But eventually, things will settle down. I'll have some ice left. I'll have some liquid in there, and I'll have some vapor. Water vapor, no hydrogen or oxygen, just water vapor, right? Because there's no air in here. Above it, there's only one thing in there, water, okay? And when it comes to equilibrium, all the chemical potentials of these different phases have to be equal to each other. And let's say this happens on mornings like today, in fact. Let's say I have just some vapor in here, so the temperature is such. The temperature and pressure I can adjust so that I just have water. Maybe there's some air in there, but it doesn't really matter. There's water vapor in there, and some temperature. There's no solid, there's no liquid. And then I lower the temperature. What happens? I mean, you come out and get in your car in the morning. What do you look at when you look through your windshield? You might have some drops of water, right? This is condensation, right? Because as I lower the temperature, the chemical potential of the liquid phase goes up compared to the vapor phase. And we have this picture, which I've drawn a couple times. I'll draw it again here. And I'll draw it yet again, and I'll probably draw it again after that. Where we had the mu of the solid, right? The mu of the liquid, and the mu of the gas. And this picture came. Remember how it came? It came from here the pressure is constant, and then the dG is minus S dt, right? And of course, it's plus VdP as well, but the pressure's constant. That term's not there, and so these lines are and they're not lines in practice, but we're going to approximate them here. They're a line with a negative slope, and why is it negative? Question number 18 on the final. Explain why the slope of mu as a function of temperature is always negative. What would you say? Well, and what is that? Is S ever negative? Yeah, because d mu is minus S dt at constant pressure, and S is always positive. Except when S is equal to what? At what temperature? And what law is that? Okay. All right, this is just making sure. And we have a locus of points here. So what really happens is unless we have some metastability going on, those parts up there are not really there. I mean, the water has one thing, okay, and it is this kind of, it's sort of a a piecewise, it's always going down, but it's smooth except there's some kinks in it, right, where the derivative is undefined. Where instead of being smoothly bent, it's actually kind of sharply bent. It's like folded a little bit at these points of transition. Here and here. And this would be the melting point, and this would be the boiling point. So in this region, we have a solid, here we have a liquid, and here we have a gas. And so we have that picture already. So we can start doing some useful. Well, I mean, useful would be maybe a bit much. How? So if I okay, let's mention this, I guess, just in passing. Dependence of phase transitions, which is what we're talking about. So a phase transition is if I'm changing the temperature and it decides to melt. Okay, that's a phase transition. And let's say not that. On pressure. Okay, so we have this. So how does this picture change if I change the pressure? And any cooks in the audience? Okay, yeah, this guy likes to cook. I went to the same conference that I went to when I was gone for a few days, which was in Telluride, Colorado. I went to this conference in the mid-'80s. Same one, okay? And a guy, it was very different back in the good old days. And there was this crazy guy there who looked like he was in ZZ Top, okay? And this guy fancied himself as an excellent cook. And he loved Spain. So he drove all the way from West Virginia with a ham he got in Spain and all the ingredients to make paella for, I don't know, 80 people. And what is the basis of paella? It's rice, okay? And what happens if you try to cook rice and you're not at sea level, but instead you're at about 9,000 feet? And you cook the rice for, like, you read the recipe and you cook it for, I don't know, 40 minutes or 30 minutes. What do you think happens when you do that? What do you have to do if you're going to cook rice at a high altitude? Well, a pressure cooker would help, but you need to cook it a lot longer, right? So, obviously, there's something going on when you make rice at a high. I mean, and the paella was terrible. It's not supposed to be crunchy, okay? This happened. What matters is when I'm cooking rice, I have boiling water, right? And if I have water on the stove and it's boiling, what is the temperature? If I put a thermometer in the water, what's the temperature supposed to be? It's around the boiling point, right? And it's like things. There's always practical things that come into play, right? But the temperature is not the same everywhere in the pot, for instance. But if it's boiling away, it's basically at the boiling point. And at a high altitude, the boiling point is lower, isn't it? So how do we understand? That's what we're going to try to understand here. So let's. Well, I'm gonna. Okay, so we can understand that one, but I'm gonna talk about this one, liquid, solid liquid. So there's the two curves, right? And they cross at this point here. I'm sorry, the melting point, the fusion piece of that. I spent half of my time trying to get this iPad to work. And so, and we're at P equals P naught, okay, 1 atmosphere. And I'm going to increase pressure. So my DG, and I better be a little bit more consistent. But my d mu, right, is minus s dt plus b dt. And if these were, that would be true as well. dg, I've said dg is minus s dt plus b dp. But if everything was for 1 mole, like the entropy of a mole and the volume of a mole, then I would be, for one component, I could call it mu. So I'm going to, because I'm drawing this thing with mu, I'm going to do that. So if I increase the pressure, how does mu change? It increases, right? So P increases implies that mu increases, and the slope is V, right? And that's the molar volume. So do they increase the same? It depends now. It depends, doesn't it? Right. So if one phase has a different molar volume than the other, then the pictures are going to change differently. So let's take an example. I'll say, let's say the molar volume of the solid is less. And this is the typical case. Less than the molar volume of the molar volume of the solid is less than the molar volume of the liquid. There, I got it out. So which one is higher density? Let's think about what this is saying to us, right? Density is mass over volume. That's the first scientific equation I ever learned in the 5th grade, and I still remember it. We still give that. We give that problem on a Chem 1 exam. But the density, rho of the solid is greater than the rho of the liquid. This is density. So whatever this, does the ice of this stuff float or sink? It sinks. So we have a situation like this. The solid sinks. So this is not water, okay? And if I draw this picture again, so this is mu solid, mu liquid, and this is at P equals P naught. So what did I say? I said the volume of the solid is less than the liquid. So if I draw a new line, so that's mu solid for P greater than P naught, and then I do it for the liquid. Here's mu liquid, P greater than P naught. So here, I should have used different colors, and it's not too late to do that. So here's the melting point at P naught, and here's the melting point at P greater than P naught. So what happens to the melting point for this material? It goes up, okay? So at high pressure, this stuff is less likely to melt. And why is that? You can kind of, you're pushing on it, and if the volume of the solid is less than the volume of the liquid, if I take the solid, I want to make it bigger. This is very intuitive. If I want to make it bigger, the more I'm pushing at it, the harder it is to do that. So, Le Chatelier or something like that, right? So if I'm pushing harder on it, it's going to tend to want to be the solid rather than the liquid, and so the melting point is at a higher temperature. But for water, so the V of the solid is greater than the V of the liquid. So the density of the solid is less than the density of the liquid. Ice floats, right? So we have this situation. Right, that's ice floating, and that's the solid sinks. I draw my picture. Now my as I increase the pressure, the this one goes up a little bit. Oops. But this one goes up a lot more. So this is mu solid P greater than P naught. This is mu liquid P greater than P naught. And so that the point is lower. So if I squeeze ice, it wants to melt. Now I don't know. I didn't see this in this book. This could well be false, but it's a good lie. How does ice skating work? Yeah, you've heard this, right? You know, you've got the ice blade. Do people ice skate in Southern California? There must be. You can do anything in Southern California, but it's more common back in places like Nebraska or upstate New York. I went to graduate school at Cornell. So University of Nebraska and Cornell University. I spent a long time in Nebraska, and what is the nickname? What do you say when you go to a Nebraska football game and you want them to win? You say that, but there's another thing you say. You can say, "Go Big Red," okay? So I watch the games now, but back then I was so happy to get away from these idiot athletes, right? Because I was a scientist. I'm at Cornell University. I'm looking up, and there's a sign, "Big Red." That's what they say in Cornell. But they begged people to go to the football games, and at Nebraska for like decades, every game has been sold out for decades. Now, what is it hard to get tickets for at Cornell? Hockey, okay? Didn't you ever see that movie, Love Story? You know, that sad story where, I won't tell you why it's sad, but there's Cornell is playing Harvard or something hockey game. Anyway, so hockey works because, as you were alluding to, you have a blade. And for me, the pressure would be higher than most of you. You apply a high pressure to this ice surface, and it's frozen, right? We're below freezing, but then in that region the pressure's higher. So what happens to the melting point? The melting point goes down. So at that cold temperature, yeah, you got it. Yeah. So the ice will melt, and then that thin layer of water provides the lubrication that allows you to smoothly and effortlessly skate on that ice surface. So if you're on a planet where there's like solid carbon dioxide or something, yeah, so skating on anything but water, because that's the one anomalous thing. It would be kind of a drag, as they say. At least they said it back in the old days. All right, so let's move on here. And so we can draw a picture, and you've seen these pictures before. This is a phase diagram. And let me just draw it here. Looks pretty odd, we have to explain all these features. And so these lines are the lines there's an I in lines. So add it here. And here's another definition for you. I think we'll call them phase coexistence lines, which means that on those lines, phases coexist. But off the lines, they don't. Okay, that's sort of logically. So these are borders, right? And they're these lines. They're not walls. They don't. They work in a different way than the big, beautiful walls that are often in the news. And they separate regions where there's only one phase. So let's figure out what. So we're talking solids, liquids, and gases. Any Kurt Vonnegut fans? Yeah. What was that book? Where there was a form of ice, ice 9. So if you look at the phase diagram of ice and you go way off this picture, and the pressures get really high, you have one structure of ice, and then a different structure of ice. They're packed differently. And there's phase transitions between those structures. And this Kurt Vonnegut book, if I remember correctly, there was some structure of ice that if you put it in contact with any water, it would just catalyze all that water to form the same phase. So it's sort of apocalyptic in that sense. Well, let's figure out where our more normal phases are. And this goes off, let's say, like that. So where's the solid, where's the liquid, where's the gas? So what favors so I've got pressure and temperature. So do high temperatures and low pressures favor solids? Solids. Yes. Okay. So low temperature, high pressure, this is solid here. Low pressure, high temperature, this is gas. And in here is liquid. And this wall has yet to be finished. Right? So there's a point where where there was an election, and they didn't keep extending that line. Okay, so we'll talk about that point in a bit. But these lines here are where we have the coexistence. So here, this is solid gas. This is liquid gas, and this is a solid liquid. And we can understand the picture, of course, by the chemical potentials. So if I have stable solid, I have mu solid is less than mu liquid, and mu gas, right? So the solid is the lowest of the three. Over here, I'll just say mu gas is lowest. And over here, mu liquid is lowest. And that's why we have solid, it's those stable phases. Along this line, mu solid equals mu gas. Along this, and if I make a mistake, please let me know. Mu liquid equals mu gas along that line, and here mu solid equals mu liquid. And that picture that I drew, this is what they call the triple point, where mu solid equals mu liquid equals mu gas. So in that experiment I started with, where I had a block, I had some water and some liquid water, I had some piece of ice, and I had pure water vapor with a given pressure and temperature of this system. Okay, those are the parameters. That's where I would be at that point, because solid, liquid, and gas all must have the same chemical potential if they're not changing the relative amounts. If I'm away from there, then I would move on that. I've moved spontaneously. Spontaneously, what does that mean? Something that's spontaneous, yeah. There would be a delta mu negative. But what is on your list of concepts? There's the last concept. What was it? Don't forget, underlying everything, delta S of the universe being positive, right? So something that's irreversible, delta S of the universe is positive. Spontaneous is sort of a synonym of irreversible, but people say it all the time, so I thought I should mention it. It's on your the list of concepts. So. And this point here, which is, I'm going to make it purple. What do they call that? Critical point. And you know, it's kind of, there's sort of a phase fluidity kind of thing. You know, it's sort of a, if I'm up here, if I'm over here, it's pretty obvious if I'm a liquid versus a gas, right? So there's a gas up here, and it's pretty diffuse. The density of the gas is low, and my liquid has a much higher density. But if you think about what a liquid is, a bunch of randomly oriented molecules, right? They're not packed in a crystal. Solids and liquids, you know, they look very different. But imagine taking like a rubber sheet, okay, a balloon, if you will, and putting a bunch of random dots on the balloon, and that'd be your liquid. And then you could kind of start expanding that. It looks a lot like a gas when you just make the distances bigger. And imagine taking a gas and compressing that. And so it's random, right? Everything's random, but they start getting kind of close together. And then you can say, yeah, you know, I don't know anymore. You know, is this a gas or is this a liquid or a gas? And that's what's going on out here, right? And there's a point along this coexistence line. So if we're along that line, we have liquid and gas. And we'll say more about this. I like to talk about it, right? I like to talk in general. We're on that line. We have a liquid and gas, and we can tell them apart. We can tell them apart. We can tell them apart. But now we can't tell them all their physical properties. The density of the liquid and the density of the gas. They kind of coalesce, and they lose their distinction. Okay, and there's a phase, like if we move along that line, there's a phase transition that happens there. I'm not even going to write this down. They call that a second order phase transition. But if I take liquid and I just heat it up and it boils, that's a first order phase transition. So this is like a more subtle phase transition. And I'll tell you, theoretical physicists, at least back when I was in grad school, and especially at Cornell, there were famous people there, they were obsessed with this second order phase transition. I never got so much into it. There were other things that life has other things that are more interesting, in my opinion. But anyway, let's talk about a line here. So I have my P and T, and I draw my coexistence curve. And I have my, I'm going to be, I have an alpha, this is the alpha phase, and this is the beta phase. And up here, of course, mu alpha is less than mu beta. Over here, mu beta is less than mu alpha. And I could imagine, let's say I start at point A and I start at point B, and I move along that line. So I do an experiment. I hold the pressure constant, and I start raising the temperature, right? And I have a bunch of alpha here. And what happens when I reach that curve? You know, the alpha starts changing into beta, and I could sit at that point. And remember, if I'm adding heat, remember this graph? I'm not going to draw it again, but I drew this curve where I had heat, temperature, and heat added, right? I'm adding heat, adding heat, adding heat, adding heat. The temperature goes up, up, up. And that's what would happen until I hit that line. Then I add heat, and the temperature doesn't change. You sit at that point here. You'd sit right here. I'm adding heat, I'm converting alpha into beta. Once all the alpha's gone, then I start, the temperature starts going back up. But what I'm doing here, I'm actually messing up a picture. I have mu alpha equals mu beta. That's a curve, okay? And so I want to find equation for that curve. And what is that? That would be, P is a function of t. I want to find P as a function of t, so I can, in Mathematica, right? By the way, we're approaching the thing that Shaka, one of my Shaka jokes will be made more relevant in a little bit here, but probably not today. I want to find that curve. Well, I could do it because I have mu alpha as a function of t and p equals mu beta as a function of t and p, right? So I have one equation and two unknowns. And I could solve that equation to get t, or p as a function of t, right? In principle. But in practice, I could solve for p as a function of t. But, they're transcendental equations or something. No thanks. It's easier to derive a differential equation. So I can take d mu alpha equals d mu beta, and d mu alpha. So that'll give me a differential equation for that curve. Then I can solve that differential equation. Is minus s alpha dt plus v alpha dp. These fancy extra tips you get for your Apple Pencil, they don't last forever, do they? So mine's wearing out. But anyway, I have these two equations, and so S of alpha is the molar entropy of alpha, and S of beta is the molar entropy of beta, and V sub alpha is the molar volume of alpha, and V alpha is molar volume of alpha, V beta is molar volume of beta. And you can think about it like so. Well, we can rearrange this thing, and so this is always true, and along that curve. So along the curve, this is true along curve. Otherwise, it's not true. And I can massage this, and so I can say minus S alpha dt plus V alpha dp is minus S beta dt plus V beta dp. Or I can play around and I can get that if I make a mistake, which I often do. But if I do it right, I will get this. dp dt, that's my differential equation, equals delta S over delta V, where delta S is S beta minus S alpha, and delta V is V beta minus V alpha. And so S alpha and S beta and V alpha and V beta, all four of those things, they depend on temperature and pressure. But in some local region, they're constants, and you kind of have a feel for it. Like if I'm going from a liquid to gas, okay? So alpha's liquid, beta is gas, right? So let's say alpha is liquid, beta is gas. So what is delta S? It's S gas minus S liquid. Which is bigger? Is the entropy of a gas or bigger than the entropy of a liquid, or are they the same? Right, this is greater than zero, okay? And what is delta V? It's V liquid, or V gas, I'm sorry, minus V liquid. If I have 1 mole, you've done, what is 1 mole of there's like 22.4 liters for some mole. I can't remember exactly what. But the volume of a mole of liquid is a lot smaller than the volume of a mole of gas. So that one's also greater than 0. And so that tells me, for one thing, dP dt is greater than 0. And that's the way I drew the curve, isn't it? And so I could solve for p as a function of t, and if it's a straight line, and everything, in a small enough region, every curve's a straight line. Then that would be the approximation saying delta S and delta V are both constant on the scale of my plot. Then I have an equation for a line. And of course, there's always the y-intercept that's not determined by the slope. So you have to put in some initial condition. You have to have some condition you put in to actually do this. But we don't have to go. We don't have to go there. Now, delta S is a little, I'll say, awkward in practice, right? And we can use that, delta mu equals 0 on the coexistence curve. I've written a symbol that I haven't defined. Delta mu is mu beta minus mu alpha. And it's like delta, it's essentially delta G. So if delta G is negative, will happen spontaneously. So if I were on the picture in the wrong phase, I'd spontaneously become the other one, right? But along that curve, this is true. And of course, this is delta H minus T delta S. And that small h, just to be consistent with what I've been using, this is the molar change in enthalpy, right? But we could write it delta H minus T delta S if you feel better about it. And so if delta G is delta G is equal to delta H minus T delta S. If delta G is equal to 0, that means delta S is delta H over T. Right? And heat divided by temperature is we know that's entropy, right? And so my dP dt is delta H divided by T delta V. Now, now H we have an intuition for, and V we have an intuition for. So I can go back and look at this picture. We talked about how mu depends on pressure. And so here's our phase diagram. And this has dP dt greater than 0. So the slope is positive for that curve, and that's the generic case. And this is solid and this is liquid, right? So solid going to liquid, delta V is greater than 0 usually, right? And delta H is greater than 0. And why is delta H greater than 0? Usually, almost always, because I need to break the bonds holding things together in a solid. I need to add heat to disrupt the bonds between things, and so in that case, of course, T is positive, but for water, solid going to liquid, delta V is negative. right? And so if I draw this picture, PT, right, that slope, so this is H2O. I can't even read that. What does this say? My magic marker's gone into this. So this is, and this is for water. So that backward tilting slope comes about because we have that delta V being negative. Now, you know, these lines are very steep, right? So this line is steep, and this line is not steep. And why is that? So, I mean, how big is delta V for a solid to a liquid? It ain't zero usually. It actually could be zero, but it's pretty small, right? So we have a small denominator, and that slope is very steep. But if I go from a liquid to a gas, that's a pretty big. That's typically a pretty big delta V, right? And the denominator is big, and so the line is not as steep. Okay, let's stop, and we'll come back to A.J. Shaka's favorite equation. What is A.J. Shaka's favorite equation? The Clausius-Clapeyron equation. That's what we'll do next after the exam.
So I need help with the question 3 on midterm 1.
Okay.
We need to go over that problem and get it solved.
So this afternoon?
Yeah,
All right,
this
okay, yeah.
Yeah, please, thank you.
Oh yeah, sure.